In this video, we're going to do example 5. This is a little bit more complicated because we have 2 blocks instead of 1. 2 blocks are connected by a string that hangs over a pulley. If M1 equals 3M2, solve for the tension in the rope and the acceleration of the blocks. Okay, this is a 2-body problem instead of a 1-body problem. That means that we have to draw 2 motion diagrams and 2 free body diagrams, one for M1 and one for M2. Now, there's some tricks that we can use to solve this problem, and I'm going to talk about those now. It says here, solve for the tension in the rope and the acceleration of the blocks. Here's the thing, if both of these blocks are connected by one rope, in other words, the rope is attached to one end of the block and also attached to the other end is attached to the other block, then that means that the tension in this rope has to be the same. These blocks have to pull between themselves, between that rope, equally. Okay, so because it's an action-reaction pair. So since that force is distributed through the rope, that force that's distributed is called the tension. So that means the tension, at least the magnitude, will be the same for the rope because the rope itself isn't changing. That also means that the blocks are going to be moving simultaneously. And because the blocks are moving simultaneously because they're connected to the same rope, that also means that their accelerations must be the same magnitude. Now you may be thinking, but Dr. H, that doesn't make sense. How can you have a block of mass m and a block of mass 3m2 be equal as far as the acceleration? How can they have the same acceleration? Well, it's the same thing as saying that you have a very large adult that weighs 180 pounds pulling a wagon or accelerating a wagon from rest, which weighs 50 pounds. You're applying the same amount of force, and therefore both objects are connected. They act as one object. And so one may be going down and one may be going up, but they're still connected, and therefore the magnitude of the acceleration has to be the same. Okay, so what I'm going to do is I'm going to go ahead and draw a picture of this. Pictures always make these problems easier. Okay, and I'm going to rotate my camera just a little bit so it's easier for me to write. There we go. Okay, so let's go ahead and draw a picture for problem 5. Here is what we have. We have a mass hanging on a rope that's attached to a pulley, and there's another block. Okay, this is M1, this is M2. And we know that M1 is equal to 3 times M2. That means that M1 is heavier. Now, you may be thinking, well, of course that's true because M1 is lower than M2. It doesn't matter. I could have labeled this M2 and labeled this M1. So the size of the block doesn't matter when it comes to these problems because you can have a different density. Okay, and it'll still give you the same answer. Okay, so here we have our 2 blocks, and what I'm going to do now is I'm going to show you a trick. I'm going to fold my paper in half, hot dog. Okay, so I folded my paper in half, hot dog. And what I'm going to do here is I'm going to put M1 on this side and M2 on this side. And that way I can keep both blocks straight. Okay, so block M1 is going to be heavier than M2. So that means it's going to move down. So this is going to be the direction of our system. Block M1 is going to go down, block M2 is going to go up. So let's go ahead and draw the motion diagram and the free body diagram. Now remember, because they're accelerating the same, the change in the velocity is also the same. So if I start from rest, I'm going to increase each one by a half a centimeter. Now, you may be thinking, well, they're falling. One's falling Therefore, it has to have the same exact acceleration as that due to the Earth, the acceleration due to gravity. Unfortunately, that's not going to be a correct thought because you're forgetting one thing: the rope. The rope is pulling upward. The Earth is pulling down. So there's another force in that system. Therefore, the acceleration cannot be that due to gravity. So we're going to have our velocity increasing. I'm going to go ahead and draw my my acceleration. For this one here, I'm going to have it directed downward. Okay. And then what I'm going to do is I'm going to go ahead and draw the same motion diagram for M2. But here's the difference. It's going to be the same values, but in this case, it's directed upward. Okay, so there's my motion diagram for both blocks. M1 is going down, M2 is going up. So now I'm going to draw the free body diagram. What's physically touching M1? The rope. What's physically touching M2? The rope. What's acting at a distance on both blocks? The Earth. Am I in equilibrium? Be careful. No, I'm not in equilibrium because I have an acceleration. Okay, here's the other thing that can give you the hint on that. It asks you to solve for the acceleration. They never ask you to solve for something if it's 0. Okay, so if they're asking you to solve for a numeric value, then you know that you have to have that thing. If they ask you conceptually, what would be the acceleration of M2 compared to M1 in this problem? You should say it's the same. Okay, because the two blocks are connected by the same rope. Okay, so let's go ahead and draw our motion diagrams. I'm sorry, our free body diagrams. We're going to do that with a dot. Now, remember that M1 is 3 times M3. So that means its weight has to be 3 times greater. So I'm just going to make the weight 3 centimeters long. And I'm going to make the tension 1 centimeter long. Actually, I better do 2. Let's do 2. Okay. Over here, I'm going to make this 1 centimeter long. And I'm going to make this 2 centimeters long. Now, why did I make this tension 2 centimeters long? Yeah, this tension is also 2 centimeters. And what did I tell you? It was going to be the same tension in the rope. So what's different here? It's the weights. Okay? If I take 3 minus 2, what do I get? I get 1 down. If I have 2 minus 1, I have 1 going up. Okay? So notice that in both drawings, I've drawn them to scale. Okay? The weight is 3 times the other one, and the tension is the same, and the difference between these two lengths will give me 1. For this case, it will give me 1 going down. In this case, it will give me 1 going up. So when you draw these free body diagrams, you really need to make sure they are to scale. Okay, this is one of the things that they may ask you to do on your AP test. Okay, so let's go ahead and label this. This is force on M1 by Earth. This is force on M1 by rope. This is force on M2 by rope. And this is force on M2 by Earth. Okay, so now what I'm going to do is I'm going to go ahead with Newton's second law. So the sum of the forces in the y direction is equal to MAY. And so now I'm going to substitute in for my free body diagram. I have force on M1 by rope plus force on M1 by earth, and that is equal to M1A. Am I accelerating? Look at your free body diagram, look at your motion diagram. The answer is yes. Okay, so I'm going to put a little check here. Newton's first law. Now what I'm going to do is substitute in magnitude and direction. So I have force on M1 by rope, J hat, minus M1G, J hat. Now, what is the direction of the acceleration? It's going down. So I need to make sure that I put a negative here, and this is M1A, J hat. This is where students end up getting the wrong answer. This one little thing right here, they don't put the negative in. Okay, so we're going to cross out our J hats. And we're going to go ahead and solve for nothing. I'm just going to leave this. Let's write it out. Force on M1 by rope minus M1G equals M1A. Now, there's a reason I'm leaving this as is. This is the tension. This is the weight. Here is my acceleration. Can I solve for the tension? No. Can I solve for the acceleration? No. And why not? Because I have two unknowns. How many equations do I need to have if I have two unknowns and I want to solve for those two unknowns? I need two equations. So I'm going to need another equation. So I'm going to go over to M2 and see if M2 can give me the answer. Okay, so we're going to start again. The sum of the forces in the y direction is equal to MA sub y. Substituting in for my for my free body diagram, I have force on M2 by rope plus force on M2 by earth, and that is equal to M2A. Am I accelerating in the in this problem? Yes, I am accelerating. Newton's first law. Okay, so I'm going to now substitute in magnitude and direction. I have force on M2 by rope, J hat, minus M2 G J hat is equal to M2A J hat. Notice here I don't have a negative because this is going up. It's accelerating upward. Crossing out my unit vectors. Now I'm ready to look at my equation. I have F on M2 by rope minus M2G is equal to M2A. Okay, now how many equations do I have? 2. How many unknowns do I have? You may be thinking 3, but remember, the tension is the same. So F on M1 by rope is equal to F on M2 by rope. Okay, so we have two equations. What I'm going to do is I am going to solve for the acceleration by elimination. So I have force on M1 by rope minus M1G equals M1A. Negative. Oh, look, I almost forgot. Negative. See, I didn't bring it down. So you probably caught that, and you were just like, wait a minute, Dr. H. But I can't hear you. I'm on video. Okay, and now I'm going to subtract this second equation. F on M2 by rope minus M2G is equal to M2A. But I'm subtracting the whole equation. So force on M by rope minus force on M by rope gives me 0. And then I get M minus M1G. Here I get a negative and a negative, I get plus m2g is equal to negative m1a minus m2a. Okay, I'm going to factor out an a. Okay, so I end up with equals negative m1 minus m2 times a is equal to negative m1g plus m2g. Okay, now I'm going to divide both sides by negative m1 minus m2. So I'm going to divide both sides by this term, and I end up with a is equal to negative m1g plus m2g, all divided by negative m1 minus m2. Okay, this is solving for a, but I also know that m1 is equal to 3 times m2. So I'm going to go ahead and substitute this in for all my m1s. So the acceleration is equal to negative 3 m2g plus m2g, all divided by negative 3 m2 minus m2. Negative 3 plus 1 gives me negative 2 m2g, all divided by, now negative 3 minus 1 is negative 4 m2. Notice that the m2's cancel out. Notice that the negatives cancel out. And notice that this gives me 2 in the denominator. So what is my acceleration? G over 2. Okay, so writing this down, for block M1, the acceleration is going to be equal to negative G over 2 J hat. For M2, it's going to be A is equal to G over 2 J hat. Okay, now we need to find the tension. What is the tension in each rope? Okay, if we go back to our previous equation, we know that F on M1 by rope minus M1G is equal to minus M1A. We can substitute in the magnitude of A into this equation, which would just be G over 2. So this is equal to negative M1 G over 2. Now what I'm going to do is bring this to the other side, and I end up with F on M1 by rope is equal to negative M1 G over 2 plus M1 G. And what does this give me? It gives me M1 G over 2. So, force on M1 by rope is actually equal to force on M2 by rope because they're both in the same direction. And that's equal to M1G over 2 J hat. Now you may be thinking, well, wait a minute. This is M1G divided by 2. But remember, when you multiply M1 by G, you can take the whole numerator and divide by 2. So writing it this way is the same as writing it this way. Okay, and there is your answer for the tension, and there is your answers for the accelerations.